Alright, silly people, here's the situation. We're going to be doing the sunspots.txt data file from the online resources again. First of all, just plotting it and making an estimation of the periodicity of it, but then also actually doing the Fourier transform of it to check, what the frequency is and if it matches up with the sunspots data. So, okay. Um, First step is, as always, we're going to import numpy as np, obviously, and then use it to read in the sunspots data, right? So I'm going to create a data thing called suns, which is going to be the numpy load text object of sunspots.txt. And we can very quickly use matplotlib.pyplot to plot it, right? So I'm just gonna lt.plot the entire first column versus the entire second column of the data. And so yeah, that's what sunsplots look like. We've seen it before. The thing to look at this, though, is to figure out how many cycles happen per month, or how many months it takes to do one cycle, basically, because this is definitely a wave of some sort. We can Fourier transform this. And I'm thinking that the length of a cycle, since I'm counting 1, 2, or actually 1, 2, 3, 4 full cycles in a span of 500 months. So that's like 500 months per 4 cycles. I don't know. It's like 5/4 times 100 months in a cycle. So like almost 100 cycles, or almost 100 months per one cycle, but not quite. It's a little bit more than that, like 125 months per cycle, I would say. Not that that's going to actually tell us anything. We're just estimating the length, but now we're going to actually Fourier transform this guy. So let me copy down this cell here, and then also make sure to run the DFT of y function that's up here. This is also on the online resources. And just run the data through it. So let's call the coefficients of the Fourier transformed version of the thing C suns. Run it through DFT, particularly the second column is what you want. 1 comma or colon comma 1, and then we can also plot that. We can plot the absolute value of C suns and see what we get. It does take a second for the DFT function to run because it's really slow for this part of the book. Okay, here it is. So yeah, you see that there is a non-zero peak for the frequency up in here. So somewhere in like between 0 and 200, basically, there's a peak there. And what we want to do now is we want to find the k value which corresponds to that peak. So to do that, let's just run through the thing. So I'm going to take the C suns data, and I'm going to say for k in range len C suns, but also not starting at 0 because it's just going to pick up this for the maximum if we start at 0. So let's start at like 10. Create a variable called kmax, and initially set it to 10. And while we're going through this range here, we can check if the C suns indexed by k is greater than C suns indexed by k max. If that's the case, then we change k max to k. Otherwise, you just keep going. So at the end, we'll have it print what it thinks k max is. And also, just to go ahead and clarify the absolute value of this, right? Yeah, something like that. And so I see that it printed 26. It found the maximum pretty quickly. So it's telling me that this peak is happening at k equals 26, which I believe it. How do we turn that into a sine wave, which is what the next part of the problem is, which I forgot to paste here. But yeah, we're basically going to take the original plot of the sunspots data, so this stuff, and also plot on top of that a sine function with a frequency that we solved using this k max value. Of course, the frequency is going to be 2 times pi times k over L, where L is the length of the data, so let's create L equals len of suns. Let's just make it the length of the domain. And then we pretty much just plot, or actually create a x variable called linspace from 0 to L in 1000 steps. And then in here you plot x versus the sine of x times the frequency, which is k max times 2 times pi, or np.pi over L. And I'll tell you right now, this is going to look weird unless if we make the amplitude quite big so that we can actually see the oscillation, and all we're really checking for is the frequency of the wave anyway. So I'm going to make the, I found a good value that works is making the amplitude of the wave 75 and also taking it up 75 points above the x-axis so you can match up with the wave. And so with that, we can plot it, and you can't, it is hard to see really what is going on here. But if we zoom in on let's do 0 to 1500, that would probably be easier to see. Yeah, so our sine wave in orange is peaking here and here and here and here and here. It kind of doesn't have the periodicity like in this region here, but you can see that for most of the graph, our frequency of the sine wave is matching the frequency of the data. So our Fourier transform did end up making sense for this guy. So, okay, what a nice problem.